Good evening, everyone. Welcome to the 12th assignment of the course Network Analysis. Today is the last assignment, and we have one more week left because this is a 12-week live session. And since the course is running 1 week ahead of this live session, so that is why we were, doing the assignments. I mean, of the next week. So, since we'll be over with the assignments today, for the last live session in the next week, we will look at some typical problems of the entire course. So, I will choose some, noteworthy problems from some references that I can get, and we will try to solve them. And by that we'll be concluding the live session of this course next week. So anyways, so today's assignment number 12, it, as you might be knowing, it deals with operational amplifier circuits. So these are nothing but amplifiers that tends to amplify the input signal, and we will be looking at this. So I'll share my screen. I hope you are able to hear me. Uh, can anyone just let me know whether they are able to see the screen and hear me?
Yes, sir. Screen is visible and you are also audible.
Okay, okay, thank you. So, as you know, if you have gone through the the basic electronics course, or analog circuits rather, not basic electronics. If you have gone through the analog circuit course, which is also another course, uh, compare network theory is a big subject in electrical engineering as well as analog circuits. So there you will be reading in detail about the operational amplifier. But today in this course, the operational amplifier circuits, will be looking at some of the basic concepts, and then we will try to solve the problem. Because for the assignment, I don't think you need in-depth knowledge about operational amplifiers. So before going into the these assignment problems, we will look at some of the basic concepts. So basically, so an op amp, it looks like this, right? So it's basically a triangle where you have these, you know, ports or connections, you may say. So this terminal here, so basically you have what, one, two, three, four, five terminals. So we give each of these terminals a name. So here this is written as minus and this is plus. So this minus terminal is written as the inverting terminal due to the negative sign, and this plus terminal is represented as the non-inverting terminal. Now this on the top, it is written CC, and this at the bottom is written as minus VCC, and this is written as VO or V output. Okay, so basically an op amp, it uh, so there is an IC. So this is nothing but IC. Here you get these many input terminals. So I think there are about four. So it's something like this. So these chips are available in the market, where each of these, so these are nothing but these input terminals. So here we have, so there are five input terminals, and here there are eight, because the remaining three have some other I mean important, so that we don't need to know right now. But these, for example, here this input terminal is the inverting terminal, this is the non-inverting terminal. So in this way, so this is the output terminal. So this kind of chip is readily available in the market, and their specifications are also given. So while we represent this in a circuit, we draw this kind of a diagram to represent that, okay, this is op amp. So now, so there, I mean, op amp has two configurations, or so this is an open loop configuration, or there is no feedback. Okay, so this is open loop. Feedback means what? Can anyone tell me in the audience, or in the, I mean, can anyone of you tell me what is closed loop or feedback configuration? By feedback, what do we mean? Hello?
To nullify the op-amp gain as well.
No,
Infinite
that,
gain.
yeah, you are talking in terms of the op amp, that is okay. But in general, if anyone tells you to say what do you mean by a feedback circuit, it means that the output is connected to the input. Okay, so in op amp we do to reduce the gain, open loop gain. So feedback means the output is connected to the input. Okay, so feedback or closed loop configuration and open loop configuration. Okay, so now just yeah. So now, what is the equivalent circuit of an op amp inside an op amp? So for that, we need to draw a circuit a bit large. So basically, this two terminals, the two. So these are the two input terminals as we saw, right? So these are the inverting input and non-inverting input terminals. So now these are connected with a resistance here. Okay, so this is V minus, V plus, and this is Z input, or you may also write R input, whatever you may want. And the output here, it is something like this. So there is a, a voltage source, there is a resistance, and then this is the output, and this is grounded, the other part is grounded. So this is Z out, this resistance is Z output, and this is A. So by A, what we mean, A represents the gain of this voltage source. Okay. So basically the op amp has two main important properties which you may want to note here. So firstly, the input impedance or resistance is infinite. Okay. And the output impedance is zero. So what would, so by that I mean, if input impedance is infinite, so for example we say that, okay, a current I is flowing, let's say, between the two input terminals. So we can write it as like this. So I would be what, input current would be what, it would be V plus minus V minus divided by ZIN. Now as per the property here, you see it is infinite, right? So if Zn is infinite, that means it is an open circuit, right? So therefore it is zero. Okay, so I input, I mean the input current is zero, therefore what we say, so this is an in ideal condition, this is, I'm talking about ideal op amp. So in ideal condition, if input current is zero, therefore what, so therefore, V plus minus V minus is zero, therefore V plus is equal to V minus. So this is the condition of what we call as the sorting of the input terminals, right? Virtual sorting of the input terminals of op amp, right? So I mean, going by this property, and if output impedance is 0, that means this Z output, this is equal to 0, because output impedance, that means this path is a short circuit path. And so therefore finally your V output, so this is V0, so your V output is represented as A into V plus minus V minus. Okay. So this A here, this is nothing but the open loop gain of an op amp. So this, therefore this A is equal to what? V0 is V plus minus V minus. Okay. Now in ideally, see, ideally this is 0, the denominator is 0, therefore your A tends to infinity, right? Because something divided by 0 is infinity. But practically for an op amp, practically, A tends to something 10 to the power 5, in the order of 10 to the power 5 to 10 to the power 6 roughly. Okay. So therefore, you can easily see the your V0 would be what, around, let's say if I consider 10 to the power 5, it would be something like this, right? So I mean, you can easily see. So suppose your V minus minus V plus minus V minus is, let's say, in the order of 25 microvolt. So what would be your output? It would be your 10 to the power 5 into 25 into 10 to the power minus 6 volts, right? So it would be around 2.5 volt. So I mean, see, that is why what we do, we apply a feedback configuration, or a a path connecting input and output, so as to reduce this large gain. Why? Because this, this plus VCC and minus VCC has a role to play. For example, let's say your, the difference between the inverting and non-inverting input terminal, let's say, is around, let's say it's zero point 0.5 volts. Okay. So therefore what would be your output? It would be zero point 0.5 into 10 to the power 5 volts. So then it would become 50,000 volt, right? Or 50 kilovolt. So 5 into 10 to the power 4 volts, right? But your VCC is, normally we apply plus 15 volts to plus VCC, and minus 15 volt to minus VCC. So it's like plus minus 15 volts. Okay. So if your output, if the output exceeds VCC, no, then your op amp is said to be saturated. Op amp gets saturated, and then your V0 takes the shape of your VCC. So then V0 becomes equals to VCC. So that is why we don't use op amp in open loop configuration, because if we apply any voltage at the inverting and non-inverting terminal, surely their difference would be, I mean, if it has a certain amount of difference, then your V0 would be large, because it has a large open loop gain, right? We saw A is 10 to the power 5, and if it exceeds this VCC volts, then the op amp gets saturated. So that is why we use op amp in closed loop or feedback configuration. And I hope you understood. So this was about the, I mean, what happens if we use op amp in the second part here. This part is on why we should not use an op amp in closed open loop configuration, and the first part is about what is, what is the open loop gain of an op amp, right? Or basically, what do you mean by virtual short circuit of the two input terminals? So these are the two, basic things I wanted to say about op amp. So if you have understood this, then we will go into the assignment problems now. If you have any doubt, please ask. Guys, you have any doubt? You can ask.
Sir,
No doubt,
your
sir.
what you told, all the point I understood, sir. But I
Hmm.
have doubt while doing the problem. They mentioned like virtual ground will not support for all the cases. Some cases virtual ground will not support like that
Yeah,
they
we will
told.
see that. We will see that. We will see
Ah,
that
okay, sir.
while
In the
we.
problem, we will see. Shall we
Yes,
see now?
yes,
While I
yes,
follow.
yes.
Okay, sir.
Yeah. Okay. So then we will go to the problems now. And these problems are quite simple, so we will try to finish them as soon as possible. Okay. So the first problem here, you can see that. So basically, see if your uh, I mean, first of all of these problems are in ideal condition. So in all of these problems, you have to assume that your the op amp that has been provided to you in the problem, that is in ideal condition. By ideal condition, what we mean, that so this, let us say that the voltage at this node, so this is a node, right? Because the current gets divided, there are two paths here, right? So the current at this node and the current, not current, sorry, the voltage at this node, that is node X, and here, right, here, so this is also X, right? So basically, or let us not write it as X, let us write it as node 1, okay, and let us write it as node 2. I mean, there is no node here, but still we are writing like this. So in ideal op amp, in an ideal op amp, the voltage V1, right, will be equal to V2. This you have to assume unless stated otherwise. Okay. And see, in this problem, you clearly see that V2 is grounded, right? If V2 is grounded, then it is equal to 0, and therefore your V1 will also be equal to 0. Okay. Because we already saw that the open loop gain of an op amp, the op amp is having infinite input impedance. So infinite input impedance means your open loop gain is equal to infinity, therefore no current would be flowing through this path. So okay, so through this path or through this path. Okay. I mean, not through this path. Basically, here there is a resistance, right? So within this path, there would be no flow of current. So therefore, if this is grounded, then you also have to assume that this is also grounded. Okay. So this is the basic, assumption that you have to assume in almost every problem. I hope this is clear before you go into the problems. If you have any doubt, please do ask. I'll stop here, because this is an important concept you need to understand. Is it clear?
Time, please.
I did not get what are you saying. Your voice was breaking actually. Okay,
Sir,
fine.
one more time, please.
Okay, okay, okay.
Sir, in
हाँ बोलो.
practical application, if we measure with Multimeter also we will get the ground concept there, sir. We will get any
No, no,
voltage
no,
there.
no, 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 no. As I told you, na, see, in practical applications, so in ideal case, what we saw that input impedance is infinite, right? So therefore, your the input current that would be flowing through this path would be zero. But in practical case, this said input impedance won't be zero. It would be there would be some resistance or impedance, but that would be very high. So practically there would be some voltage difference between the two terminals here. Okay, so practically there would be some, let's say, 5 millivolt or in that order. There would be some difference, but that won't be zero practically. But ideally, you can consider it to be zero unless it's stated otherwise. Okay.
Okay, sir.
So, and that is arriving because the input impedance is zero. So therefore, this path is open, and therefore this terminal and this terminal are at the same polarity. So therefore, we write this condition. Fine. So now, once you have assumed that your V2, I mean the inverting and the non-inverting terminals are at the same potential, right? So therefore you can, so let me just take another ink here. So therefore you can just, remove this part. You don't have to consider this part here. This op amp, you can just directly remove it. Once you have, proved that this condition exists, that, I mean, this is an ideal op amp, you can directly remove this op amp from the circuit, and now it becomes a very simple, KCL wala circuit. So basically now what it becomes is something like this. See, let me just draw it. So if we remove the op amp here, so this is our uh, you know V1 here, right? This is R1. um Now, wait. 1 minute. So this would make the circuit more complex. I mean, let us directly look at this circuit only. See, here let us say, okay, let me take another ink. You'll understand. So let us say that through this voltage source, a current I is flowing, right? Now current won't be entering into this path, right? Because this is grounded. So current would be, I mean, this part is not there only, right? This op amp is not there only. So this path is not present, right? So this path here, this is not present. So the current would directly be entering, going through into this path. Okay, the through this directly into this. So therefore we can now write a KVL or a KCL equation, right? So basically what, let us say that, okay, so this is node 1 only, or let us write this as node X, this point here where 1 is written. So what would be I? This is nothing but V1 minus Vx by R1. And what is the current flowing through this path to the through this feedback path to the output? It is also nothing but your Vx plus V2 minus V0 by R2. Now since these two are equal, this current, because the current is not entering into this path, right? So therefore we can directly equate this. and your Vx, as we saw that since the so this was plus, so non-inverting terminal was grounded, so this automatically the V1 or Vx, not V1, the Vx, the voltage at the inverting terminal, this also becomes equal to 0, right? So directly this becomes equal to 0, and so therefore your final equation becomes V1 by R1 equals to V2 minus V0 by R2. Now you can directly solve this. So your um, V1 was what, 4, this is 4k R1, your V2 is 2 volts, and V0 we need to find out, and R2 is also 4k. Therefore your this becomes 2 minus V0. Therefore V0 becomes minus 2 volts. So this is your answer. Okay, so if you have any doubt, you can ask. Any doubt you have, you ask. So this is the final answer. V0 is minus 2 volts. Hello? Yeah.
What about VSUP plus minus VSUP?
See, this is VSUP is the VCC, the saturation, the VCC voltage. So we saw here now. Wait, I'll explain. So here we saw, so it had these two terminals, plus VCC and minus VCC, that was set equal to 15 or 12 volts we saw. So this here is nothing but 15 volt. I mean, this is plus 15 volt and this is minus 15 volt. And as we saw, see, this will only come into the picture when your V0, when V0 is greater than plus VSUP, then your V0 becomes equal to VSUP. So we say that the op amp is saturated. Op amp gets saturated when this condition is satisfied. When this condition is satisfied, and when V0 is less than VSUP, then your V0 becomes equal to V minus SUP. Then also this condition gets satisfied. But here you see that V0 is equal to minus 2 volt, and it is greater than minus 15 volt, right? So therefore the op amp is not saturated. So op amp has a linear region. So it's something like this. So here in this graph, this is V output, this is V input, and it has a linear region something like this. And as soon as it gets, so this is VCC, this is minus VCC, not this one. Okay, yeah. So I mean, as soon as it exceeds this voltage, so it touches this plus VCC or it touches this minus VCC, the op amp gets saturated. The output becomes flat. So from then on, the voltage becomes minus 15 volt, and here it becomes 15 volt. So this is the operating characteristic of an op amp. So this part here, this is the linear region, this is the linear region, and this part, this is the saturated region, this part is also the saturated region. But here you see that the V0 is what, minus 2 volt, so minus 2 volt would lie somewhere around here, right? So this is minus 2, so clearly this part is the linear region. Therefore your V0 is equal to minus 2 volt. So basically, while solving the problem, you need to take care of this. If your V0 is greater than SUP, I mean plus VCC, or if it is less than minus VCC, then you need to implement these two conditions. Okay, otherwise you don't need to no make any changes. I hope this is clear. and why SUP was mentioned. Hello? Is it clear now?
Yes, sir. Yes, sir.
Okay. Rest of the guys, is it clear? Manikananda, Murshid, Alam.
Yes, sir. Got it, sir.
For me, it's clear, sir.
Okay, fine. Okay, so now, so this is a negative adder circuit. We will see how. So similar thing here also. Um, See, this part, the non-inverting terminal, this is grounded, right? Therefore, if this is grounded, this part also becomes grounded. Okay. So this part, the voltage. So if this is zero, this part also becomes zero. So anyways, we will represent it as node X here, and I mean, see, if, when this condition satisfies again, you can take this whole op amp out of the picture. So therefore, so let us say that this is I1, this is I2, and then the current that is flowing through this is I. So simple KCL we will apply. So I1 plus I2 equals to I. Now what is I1? I1 is um, V1 minus Vx divided by R1. Okay, right? Because this potential and this is a short circuit path, so potential at this would be same as this, right? And your I2 would also be equals to what? V2 minus Vx by R1, not R1, sorry, R2. Similarly, your what would be I would be Vx minus V0 by R3, right? So now you can equate, I mean, place these three equations. So V1 minus Vx by R1 plus V2 minus Vx by R2 equals to Vx minus V0 by R3. Now Vx is equal to 0, right? Because of the virtual short. Non-inverting terminal is shorted, right? So its voltage is 0. Therefore Vx is also by R1 plus V2 by R2 equal to Vx minus V0 by R3. So now just substitute the values. 1 divided by 4k plus V2 is also 1 divided by 3k equal to, okay, so this is also 0, right? So this would be equal to minus V0 by uh, R3 is how much? 2k, right? So let me just take it downwards. Now, so this kk gets cancelled, right? So this is 3 plus 4 divided by 12 minus V0. This becomes 6. So V0 is minus 7 by 6 volts. So this is how much? 7 by 6 is minus 1.167 volts. So this is your answer. I hope this is clear. Very simple problem, provided you understand this virtual shorting principle. So if this is clear, then we will move to the next problem. If you have any doubt, please do let me know right now. I'll just wait for a minute. Okay, fine. So now we will be looking at this problem. So Manikananda, you were talking about this where, so this is a problem where the virtual short circuiting principle won't work. Okay, so this is a problem where the virtual short circuiting principle won't work. Why? because see here, this plus terminal here, right? This is the non-inverting terminal, right? And this is the inverting terminal, right? Now at non-inverting terminal, we are applying V1, which is equal to 3 volt, which is your V plus, right? And at the inverting terminal, we are applying V2 is equal to how much? It is 1 volt, right? And um, this is V minus, right? So therefore, what would be the, so see, ideally what would happen is that, you know, the this voltage, so basically here minus V2 would appear, right? So at this point, so at this point here minus V2 would appear, but minus V2 won't appear. Why? Because at the non-inverting terminal we are applying a voltage of V1, right? And V1, and here it is V2. So in such case, the equivalent voltage that would appear here would be your V plus minus V minus, because this is a non-ideal op amp, right? Because here I mean we can't apply the virtual short circuit principle, so therefore this would be 3 minus 1 equal to 2 volt would apply here. Okay. And once it does, so therefore the equivalent voltage that it would apply here, I mean that would come here is Vd. Okay. So once it does, so you need to calculate V0. So Vd is what? It's the potential divider circuit. So it's like R2 into V0 divided by R1 plus R2, right? So once you do that, it's like 2 volt. It is how much? 10k into V0, and this is 10k plus 5k, right? So 2, 10, 15 V0. So this is 5, this is 3. So this is the final answer. So I mean, in cases where you see that I mean, you are not able to apply the virtual short circuit principle. Why? Because you see that two different voltage magnitudes are being applied at the two terminals of the input terminals of the op amp, right? So in such case, the equivalent that appear at the output would be the difference of the um, two input voltages now, which is your V1 minus V2. Why V1 minus V2? Because it's V plus minus V minus, right? I mean the positive minus the negative terminal. So that's the I mean notation that we follow in op amp. So by doing that we get 2 volt, and then it's a simple potential divider circuit. So you get 3 volt as the answer. So this is about question number 3. If you have any doubt, please do ask.
Sir, actually we are calculating VD now, sir. That is
Mhm.
actually input voltage.
Yes,
Correct?
yes, yes.
Sir, it's having any principle, sir, behind that?
I
This is
did not get
this
you.
is my
It's
question.
having. I did not get you. Repeat.
No, sir. VD you are told, no, sir. That is
Hello.
actually input voltage. Hello, sir. Are you hearing me, sir?
Yeah, 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 yeah. That's input voltage. That's the difference between the input voltage. Yes.
Sir. Sir. Okay.
Where your doubt is, I'm not able to get you. Hello.
Sir, actually, what I asked now,
Hmm.
uh, In inverting terminal, we are minus that voltage with respect to non-inverting terminal, correct? As it having
Non-inverting minus inverting.
inverting, sir. It's having some reason for doing that. I'm asking.
Reason means what? See, we saw na. So if you consider an op amp to be in open loop, right, like this, then what would be your output? Your output would be V0. So this equation here. So V0 into equals to the open loop gain into the difference between the non-inverting and inverting terminal, right? So this is also what is happening, but there is a feedback path. That's the difference only here. And why this is happening? Because see, in the previous question, or let me just draw it like this. So we saw a problem na, like the first problem that we did today. So this op amp is grounded here, and let's say we don't have a you know any voltage source here. So let this be V1. This is grounded. This is R1, R2, V0. So therefore, the potential here would be 0. Therefore, your this thing would be what? V1 minus 0 by R1 equals to 0 minus V0 by R2, right? So V0 would be minus R2 R1 into V0 V1, right? Now see here, this was grounded, right? This was grounded, but if there was a potential here, let's say V2, then this would have been, instead of 0 we would have written V2, right here. Now so now in the current problem here, we don't have any resistance in this path, right? We don't have any resistance. We are simply, so this is the problem. I mean, try to correlate this with this, right? So these two problems. So basically for this problem, inverting non-inverting are reversed. So here we have V1, and here we also have a another source which is being added as a feedback, right? So this was the problem. This is R1, this is R2, and this is V0, right? So it's basically the same if you remove R1 and I mean if we correlate these two, it's same if we remove R1 and we connect V2 to the feedback path. Okay, and all this part is removed. So what happens is that, see, you are applying one potential at the non-inverting terminal and the other potential at the uh, inverting terminal, right? Because V1 is not equal to V2. So therefore, what would be the equivalent input voltage? There would be some equivalent input voltage to the op amp, right? Because here there was 0, or here there was V2, right, that the op amp was getting, right? But here it is not the case, because V1 is not equal to V2. Therefore you need to calculate like V plus minus V minus, that is V1 minus V2. So this is the equivalent voltage that the op amp would be getting, and that is being fed to the output as a feedback. So therefore this is the voltage Vd that you are getting at the feedback. From there you are calculating V0. So this is the difference between the two circuits. Is it somewhat clear now?
Yes, sir.
Okay, fine. Fine. Okay. So, if you have understood this, then now let's move to the other problem. Okay. So, in the next problem, see here. Um, so this plus terminal is connected here, right? So let us say that this potential is, or this is node X, right? And here also, this non-inverting terminal is connected to node X, right? Not node X, it's connected to 3, between 3 and 4. So here also we can write it as X. I mean, we can apply the virtual short circuit principle here. Why? Because I mean, we can assume the op amp to be ideal in this case, considering because you can see that V1 and V2 are not directly connected to X, right? If that was the case, then it would have been 1 minus 5 volts, right? V1 minus V2, but it's not the case here. So therefore we can apply the virtual short circuit principle. So having so once you do that, so this whole part would become, you can remove this part here. So therefore we need to find out what is the potential at node X, right? Because it's not zero and it's not grounded. So if we apply KCL here, right, so this directly would flow into this path, right? Because this path, no current would flow through this path. So therefore we can clearly, I mean, simply write a KCL equation at this node. So this is what V1 minus Vx divided by R1 is how much? Vx minus, so potential here is node 2, right? So V2 basically, this is R2. So therefore you can directly find out what is Vx. So this is 1, this is Vx, R1 is how much? This is 4k, Vx, V2 is 5, R2 is 3k, right? So if you just cross multiply, this is 3Vx, 4Vx, 20, right? So this is Vx is 7Vx is 23, and Vx is 23 minus 7 volt, by 7 volt. So this is approximately 3.286 volts. Okay. So I'll just stop here. Did you understand how we calculated Vx? If you have doubt, please do ask here. I'll just stop because after that the problem is simple. Did you understand how we calculated Vx till this point? Hello. Okay, fine. So once the potential at this point is found, na, so we can directly apply KCL through this path here. So where there is this is one node, right? So if we say that, okay, let's say I dash is flowing, so therefore no current would be entering this path. So here also I dash would be flowing, right? So therefore we can easily apply KCL at this part. So V2, why? Because potential at this is V2. So V2 minus this is Vx, and Vx we just found out. So V2 minus Vx by R3 is Vx minus V0 by R4. So this is 5 minus 23 by 7 divided by 3k is equal to 23 by 7 minus V0 divided by 2k. So this is what, 10 minus 23 into 2 is 46 divided by 7 23 into 369 divided by 7 is equal to 3v0. So 3v0 is equal to 46 plus 69 divided by 7 minus 10. So let me just calculate this. How much is this? Um, so 46 plus 7 v0 is 2.143 volts. So this is the final answer. See, the critical step in this problem is to find out what is the voltage at node X, and you can directly, apply a KCL through this path, right? Assuming the ideality of the diode. I mean, potential at this node, the inverting and non-inverting are equal. So you can directly apply KCL at this path. Once it is done, after that you can directly apply KCL through this feedback path, right? Through this path and then through the feedback path. So that will give you the value of V0. I hope this is clear. If you have any doubt, please do ask. I will just wait. Guys, is this clear?
Yes, sir.
Manikananda, Satyaprakash, do you have any doubt?
Yes, sir. It is clear.
Okay.
Sir, it's clear, sir.
Okay. Fine. So let us now go to the next problem. So this is pretty simple. So this problem we saw earlier, right? See, this is also an ideal op-amp circuit, right? Where this potential at this node, right? So the potential at the inverting, I should not say node, or rather the potential at the inverting terminal and the non-inverting terminal, I should say. So this plus terminal is the non-inverting, and we are applying V2 here at the non-inverting here. And since this is an ideal op-amp, so your this would also be V2, right? Because here the resistance that is connecting the inverting and non-inverting is open. Okay. So once you do that, so the this current, right? So this current is flowing through this path, right? So once you do that, this becomes pretty simple. So V1 minus V2 by R1 is equal to V2 minus V0 by R2, right? So V1 is 4, and this is also 4. This is R1. Then V2, sorry, not V2. This is 4. Yeah. So this is also V0. And we don't need to write what is R1, R2 because this thing is 0. Therefore, V0 is 4 volts. So this is the answer. I mean, you see here this op amp. So basically, see, if there was a, so if I write it as like this, so let's slightly introspect this circuit. So if V1, if V2 was not 0, right? So just let's find out V0 in terms of V1, V2, and R1, R2. So if we just concentrate on this equation, so if I just rewrite this, V0 would be what? It would be, so it's like, you know, V1 minus V2 by R1 plus V2 R2, right? So it's like V0 is V2 plus R2 by R1 minus V1 minus V2, right? So see, what would be the gain of this circuit? It would be nothing but R2 by R1, right? But so it would be R2 by R1. However, since your V1 and V2 is equal to, I mean, they are both equal, right? Since V1 is equal to V2, therefore this thing would be equal to 0. Therefore, this is a direct, you know, the input is directly followed into the output. So it's almost like a, unity feedback configuration, you can say. So this is kind of a unity feedback configuration because of this condition. So in we can also draw a unity feedback in this way instead of using all these resistances. So suppose we have the op amp like this. So this is the input, this is the output, this is the non-inverting input, this is the inverting output. Now what we can do is something like this. We directly take this non-inverting, and without using any kind of resistance, we directly apply this to the output. So this is V0 and this is V in. Now if the diode, if the op amp is ideal, if op amp is ideal, see, potential at this point would also be equal to V in, right? Because this is a virtual short circuit. So therefore your V0 would be equal to V in, which is, I mean, which is the case also here, right? Because V1 was also 4 volt and V2 was also 4 volt. So I mean, in a way, this is also a unity feedback. Why unity feedback? Why we call unity feedback? Because the gain is one, unity. Because input is equal to output, right? So here, if we write something like this, V0 is A into V in. Here A is 1. So that is why we are writing unity. And there is a feedback here. Therefore, that is why the feedback word is coming. That is why this circuit here and this circuit here is all same. Why? Because here also V1 is equal to V0 and here also Vn is equal to V0. So that is why this is a unity feedback configuration. I hope this is clear. If you have any doubt, you can ask. Okay. If you don't have any doubt, let us proceed. Here, okay. Here you see, in this circuit, so this is V1, right? So this is also a kind of, so this circuit is same as the previous circuit, right? Only that all of these resistance and this voltage source is there, but otherwise this is nearly same as this. So basically here, since this is an ideal op amp, so this V1, I mean, the potential at the inverting and non-inverting would be same, right? So therefore, the potential here, the potential here at this point. So if I write it as node A, so node A, so VA would be equal to V1, and therefore, I mean, we can totally ignore this circuit and let us just redraw this part in something like this. So here, this is V0, this is what R1, this is V2, this is R2, right? This is V1, R1, this is V2. And now the potential across this, right? I mean, the potential at this node with respect to ground, right? Because this is ground. So va would be what it is, v1, right? So basically this node. So I can redraw it something like this, right? So this is v1, because the I mean this the potential at the non-inverting terminal is equal to the inverting terminal, which is equal to v1, and it is applied at the node A, and node A is our this node. Therefore the total potential across this v2 and r2 would be equal to v1, right? So this is the equivalent circuit. So from this we can now calculate what is V0. So we'll calculate this, but before that I'll just stop. So guys, did you understand this? How we have redrawn the circuit from this to this? Is it clear?
Yes, sir.
Okay, fine. So now once we have done this, so the remaining part is pretty easy. So what would be, see, this current I would be flowing, and the same current I would also be flowing through this path, right? So I mean it is similar to the previous problem. So v0 would be what? It would be v1 plus ir1, or, and on the other hand, what is v1? It is v2 plus ir2, right? So now from here you can calculate what is I. So it is V1 minus V2 by R2. So I is what? V1 is how much? It is 4, and it is 6. And this is R2 is how much? This is 4K, right? Sorry. Right. So I is how much? I is uh, minus half, I mean minus zero point 0.5 milliampere, right? So once you have done this, you can easily now calculate. So v0 is what? V1, that is 4 plus minus zero point 0.5 into r1 is 2 kilo ohm, right? So this is v0 is 3 volts. 4 minus 1 is 3 volts. So this is the answer. So if you have any doubt, please do ask, because this kind of problems you will be seeing in the assignment 12 also in some twisted manner, but the concept is the same, the method is the same. If you have any doubt, please do ask. See, you may ask that why we are considering that there is no current flowing from v1 into this node, right? Because this is a voltage source, and in the previous assignments we saw that any voltage source, it sends a current, right? But here we have assumed that in an ideal op amp, no current, I mean until and unless there is a feedback path, right? Until and unless, so for example, if there was a resistance here and there was a feedback path something like this, then a current would have flown through this path. But this is directly connected, so let me just remove this. Yeah, so this is a direct path, right, which is connected to the non-inverting terminal, and I mean we can totally, remove this part out of the circuit. So essentially it's like, I mean, the potential across this is v1, right? v2 plus I mean across this resistance plus this potential voltage source is v1. Why? Because the non-inverting terminal ka voltage is connected across this whole part. but there is no current flowing into the op amp, right? Because this is directly connected to the op amp, and this is virtually shorted, means v1 is, I mean, the va is equal to v1. So therefore there is no current flowing through this path. So this is a direct path where I is current is flowing from v0 to the ground, and your potential across this v2 plus this resistance, the drop across this resistance is nothing but the v1 voltage which is connected to your non-inverting terminal. So that is why there is only a single current flowing through this path. I hope this is clear. This step is very essential, because if anyone sees this circuit, they will definitely be applying. So this would be this would be I1, or let's say this is I1, another current would be flowing through this path I2, and this would be I3, right? So it would be something like I1 plus I2 equals to I3, and then you would be stuck, right? So I hope this is clear. Again, I'd ask you, if you have any doubt, please get it clarified.
Sir, if
Yeah.
sir, if I VA is not equal to V1, then how to solve this circuit?
If VA is not equal to V1, then it's like, it would be VD is equal to V1 minus VA. That previous problem we solved now. So if
Okay,
it's like this, so if there is another potential, so voltage source connected across this path, which is, let's say this is VB, right? So then your VA would be something like V1 minus VB, that
okay,
previous thing. So in that case, you can't apply your the ideal op amp wala theorem. So you need to find out the difference and then apply.
got it, sir.
Okay.
Sir,
Yeah.
sir, I have one doubt. Sir,
Bolo.
in inverting, in non-inverting terminal, we connected V1, sir.
Hmm.
In uh, inverting terminal, if we connect a resistor alone and ground that resistor now, the resistor means it need to draw current from it now, sir. At the case, what it will happen?
So you are saying something like this. So this is grounded, and this is something like this. Are you talking about?
No, sir. From the ground to A point, no, sir.
Huh? From the ground means from this point. Okay, so from this point to point A.
Not, sir. From the yes, sir. From the negative terminal to point A, if we uh, remove the connection, and from the negative terminal, not inverting terminal, if we connect a resistor alone, it will draw current or not, sir, with respect to ground.
So
Can I
you are
use that
just
in non-inverting terminal as voltage source? I am asking, sir, like that question. You
no,
told
no.
that it will not draw any current, no, sir.
So in this case, it won't be drawing any current, but as soon as you connect a resistance, it will draw, because there is a feedback path. But that would happen only if you connect a resistance in this path here, and there is a feedback through this path, through the non-inverting terminal. Because see, here, if you, for example, here, if I connect a resistance here, then there would be a potential drop across this, right? Across this resistor here. And your VA, then in this case, your VA won't be equal to V1. It would be something like VA minus the drop across this resistor. Something like this. So in that case, this resistance would pop up here. and then there would be another current that would be flowing through this, and then you need to calculate V0 accordingly.
Okay, sir. Sir, if we remove R1,
If we remove R1,
hello.
yes, yes.
Okay, sir. If we remove R1 and V2,
Hmm.
at the time also that at potential A is there, na, sir? That and V1 are both are equal, correct, sir?
See. Okay, let me just remove this all the parts. I got your question now. Okay, fine. So just let me remove this resistance also. So you are saying that we have removed this R1. So the equivalent circuit becomes something like this. Just correct me if I am wrong. So this is, so here you are applying V1. This is, so you have removed V2 also, right? You are telling?
Yes, sir.
Yeah. So it's something like this, right? R1 is removed and there is a resistance through this path, right? This circuit, right?
Yes, sir.
See, in
Sir,
that
if
case,
we
this
remove the short between V out to R1, sir.
V acha. Okay, fine. Okay. Wait. This becomes equivalent to the that thing na, open loop circuit na yaar. We saw na. So it's now what? Now this is what? What happens to this here? What happens to VC, the non-inverting, the inverting terminal? Because initially it is connected to, there is a feedback path. Now what do you want to say? What has happened to this inverting terminal?
It having, sir, it having one resistor with
Ah,
respect to ground, sir. That resistor is grounded.
this thing.
So now it will draw current from Apama or not, sir?
No, because this is connected to ground na. So the potential here would be what? This would also be V1, right? Because see, this is an open loop configuration only, because there is no feedback path. This is an open loop configuration. So I mean, if you still consider your diode to be your op amp to be ideal, then the polarity, the potential at the inverting and non-inverting terminal are equal. Therefore ideally your this thing would be zero, because V1 minus V plus minus V minus is zero, right? How will it draw current? It will draw current, but I mean, it may draw current, but you need to look at V0 from these two terminals, from the point of view of these two terminals, right? So, since this is grounded, the potential at this point would also be V1, right?
Yes, sir.
You need to see, Manikananda, you need to look at a circuit from this op amp circuit from the point of view of feedback. If there is a feedback, then you apply the things accordingly, but if there is no feedback, your V0 would be a comparator circuit. It will compare the input and output, so it would be A into V plus minus V minus. What is the point of connecting a resistance here? Because if you are making this potential V1 here, the potential at the inverting terminal has to be V1 also, provided you consider this to be a ideal op amp. Then your this thing, would be equal to zero, right? If unless stated otherwise. Okay. And see, if so let me just redraw this circuit once again. So if you have something like this, see, current would only be flowing if there is a feedback path, Manikananda, because you have considered the input impedance to be zero, infinite. So the you are confused in this. See, what was the inner this circuit here? It's like this, right? So it's like this. So this is V plus, this is V minus, this is Zin, and this is tending to infinity. Now here, even if you connect a resistor, what would happen at the circuit? Nothing would change, right? So this would become what? So still your V0 would be A into V plus minus V minus. So suppose you make your V0 V negative, this thing equal to 0, right? And this has some voltage, that what is you are trying to say. Even if you don't consider your op amp to be ideal, then also this equation would be valid, right? So this would be what? A into V plus minus 0 volts. That would be something like what you are saying. But no, I mean, since you have grounded this, a current would be flowing through this path, nothing else. That would get reflected onto the output. Now, if you consider your Z impedance to be infinite, then no current would be flowing through this path because this is open circuit. Is it clear now? That is why we talk about feedback paths. So in feedback path, if you connect a feedback path here, so immediately, so if we connect a feedback path like this, so potential, so let's say this is grounded, there is no V2 here, okay, there is no V2 here, so this is grounded. Even if this is grounded using a resistor, the polarity, the potential at this point would be zero because this is grounded, and immediately there would be no current flowing into this path because this is open circuit. There would be no current flowing through this path, so therefore the total current would be flowing through the feedback path.
Sir,
Is
now
it
I'm
clear now? Hello?
yes, sir, clear.
Okay. I hope, okay, in this problem, I hope you understood why no current is flowing through V1. Because this is an ideal op amp where polarity at these two terminals are equal, and therefore no current would be flowing. So no current would be flowing, so ideally there is a resistance here which is infinite, so ideally no current would be flowing through this. Therefore no current would be flowing through this path here. No current would be flowing. Therefore, we only say that the polarity across this total, this V2 and R2 is V1. This is the thing. This you need to keep in mind. You need to understand this. Bas, that's it. So see, next problem is also the same. It's very same. So here also the diode is ideal, right? And here, if we consider this resistance and this resistance to be infinite, therefore no current would be flowing through this path. This path would is virtually open. I mean, not virtually open, I should not say. I mean, no current would be flowing. So basically these are are at the same polarity. So therefore this would also be equal to your um, V1. Okay, now if this is equal to V1, so can we read the circuit something like this? So this is the initial R here, right? And this is our V1 here, right? And this is V2. Therefore, if I say that, and this is V0 obviously, So if I say that a current is flowing from V0 to ground, it would be something like this, right? V0 is equal to V2 plus I into R, right? And what is IR? IR is nothing but V1, right? Because it's the polarity potential across this resistance essentially, because the V1 is getting followed into this because there is a unity feedback path. So unity feedback means total V1 would be flowing into this, right? So now what would happen is that V0 would be equal to V1 plus V2. Therefore, this would be equal to 8 volts. So this is the answer. So very similar to the previous problem. If you have understood the previous problem, this would be very easy. Still, if you have any doubt, please ask. And again, please take note of this fact: SUP or VCC is plus 12 volt and V0 is less than SUP. Therefore, op amp is in linear region. So it's not saturated. You need to take care of this fact. Suppose let's say this V1 was something like, let's say 9 volt, right? So then V0 would have been 13 volt. So then you can't write 13, your answer would be wrong. You have to write 12 volts, because then in that case V0 would be greater than V SUP. So in that case, the op amp would go into what you call saturated state, and as a result, your final answer would be a V0 equal to 12 volts. So if so, this is problem number 7, similar to problem number 6. If you have any problem, please ask. Guys, any doubt here? I see. What my suggestion is that you please solve the op amp. First of all, try to understand in depth what are these concepts, these virtual short, then the open loop gain, these two or three properties of op amp you understand. You read any textbook or watch any video on YouTube or the lecture sessions of NPTEL, then you solve the problems and solve as much as problems as you want, especially the ideal op amp problems, and also some non-ideal op amp problems if you want to. Then your concepts would be very clear. So these are pretty simple problems, I should say. The easiest assignment of out of all the 12 assignments that you have done so far. Okay, so you just need to practice a lot. If you have, guys, if you have any doubt, please do ask. Otherwise, I'll proceed to the next problem. Okay, if you don't have any doubt, we will proceed to the next problem. And this problem here again, see, mm, it is very similar to the previous problem again. So see, V1 again, V1 here would get, you know, it would be here. So this is also V1. So we can redraw this output something like this, right? So this is R2. This is V1. So this is R1, R2, and this is also this is V2 and R3. So let's say that the current that is flowing through this total path is I1, and obviously this won't be the same as this because the parameters are different. So this would be I2, but essentially we need to find out what is V0, right? We need to find out what is V0. So V0 would be what? it would be I R1 plus I R2, and V1 is what I R2. So you can find out what is this is 1, right? Sorry. So this is 1. So I1 would be V1 by R2. So V1 is how much? 4, and this is 5. So 4 by 5 milliampere. So therefore I you have found out. So therefore V0 would be what? I1 R1 plus V1. So I1 is you have found out, it is milliampere, and I am not writing milli because anyways it would get cut here. And this is V1. V1 is how much? 4 volts. So this thing would get cancelled, and this would become again equal to 8 volt. So see, you can try to find out using this part, and also through this part also, through this path also. Both the ways it would yield the same answer. See here, you can't solve. So what if we use the second path, right? So V0 is how much? If we use this path here, it is I2 R3 plus V2, right? I2 R3 plus V2. So you need to calculate what is I2 and R2, right? Because you don't know here. What is R3 you don't know, and I2 obviously you don't know. So using this you can't solve because two parameters here you don't know. Well, three parameters, right? I2, R3, and V0 you don't know. So the first path is sufficient for you to solve the problem. Okay. So here I2 and R3 don't know. So problem number 6, 7, 8, they are the same. The concept is the same here. It's a unity feedback path to till this point, right? So here also, if you have any doubt, please ask. Guys, is it clear? Hello? Okay, fine. So coming to the next problem, it is almost similar to one of the problems we have solved here previously. So if we go back, so it's similar to this problem, only that this R2 was connected to V2, right? But now R2 is grounded, but the problem essentially remains the same. So so this is the voltage that is being applied at the non-inverting terminal. Let us write it as X, and this is also X, and in an ideal op amp these two are equal. So V plus is equal to V minus is equal to Vx, right? So now we can calculate what is the potential at Vx. So if we consider this to be I, and this is also entering, because no current would be entering if this path is open. So this would be what V1 minus Vx by R1 is equal to Vx minus 0 by R2, because this is grounded. So V1 is what? 2 minus Vx by 3k equal to Vx by 2k. So this would be 2Vx, 3Vx. So Vx is 4 by 5. So once you have applied this, you can now apply simple KCL here. So this would be I dash is equal to I dash, because no current would be entering here. So V2 minus Vx divided by R3 is Vx minus V0 by R4. So 1 minus 4 by 5 is equal to R3 is how much? It is 1k and this is 2k. Sorry, 4 by 5 minus V0 by 2k. So this is 2 minus 8 by 5, 4 by 5 minus V0. So V0 is 8 by 5 plus 4 by 5 minus 2. So 5 minus 2. So 2.4 minus 2 by 5. Minus 2, so 0.4. This is the answer. I hope this is clear. Pretty straightforward problem, similar to the previous problem. Any doubt, guys? You have? Okay, fine. So going back to the last problem here. See, again see here, in this problem, this is the positive terminal and this is the negative terminal. I mean the non-inverting and inverting terminal, and again this is being directly, this has a direct feedback to the out terminal. So since this is so we can say that your V plus and V minus is Vx, right? Because this is a ideal op amp. So this, I mean, since these are short paths, so the polarity at the inverting terminal would be equal to V0, and since this is an ideal op amp, so the polarity at V plus and V minus are same. Therefore, this would be Vx. Sorry, this would be V0. So this would be V0, right? So once you have done this, the remaining problem is very much, I mean, it is very easy. So I1 and I2, right? So basically, uh, I mean, this is equal to we don't have to write I1 and I2 also, right? Or we can write I1 and I2, there is no problem. What would be I1 plus I2? It would be essentially equal to 0. Why 0? Because see, there is no feedback path here, right? So there is no feedback path. Something like this is not there. So this and the there is no current entering through this path, right? So I, right? So if I write it as I here, why I is 0? I hope you have understood by now. So I is equal to 0 due to the ideal op amp condition. So I1 plus I2 is equal to 0. So now you can directly apply. Uh, so what would be I1? It would be V1 minus Vx, uh, sorry, V0 divided by R1, and I2 is V2 minus V0 by R2. So V1 minus V0 by R1 plus V2 minus V0 by R2 is equal to 0. Just substitute the values. 4 minus V0 by R1 is how much? It is 4k plus uh, 2 minus V0 divided by 4k is equal to 0. So therefore essentially this becomes, so 2 V0 is equal to 6. So V0 is equal to 3 volt. This is the final answer. This is also pretty simple provided you have understood the concept of ideal op amp. So yeah, so this is about today's assignment. I hope you have understood the last problem, problem number 10. If you haven't understood, please ask why, like why this I is 0, right? Why I1 plus I2 is equal to 0? Why the polarity at the non-inverting terminal is equal to V0? If you have any doubt, please do ask, because this kind of problems will be coming in your final exam that will be appearing for. Please do ask if you have any doubt. Guys, is it clear? Manikananda, Satya Prakash, is it clear to you? Okay, fine. Okay. Acha, you have some doubt. You can speak, Manikananda, if you have doubt. I think you can speak. Your mic is not disabled.
Or you wanna ask me the question also I need to understand. Or that only to answer that only I raise the answer. No doubt, sir. It's well clear.
Okay. Fine. Sorry. Okay. So yeah, that's it for today's assignment. So this completes the list of assignments for this course. In the final week, we will be looking at some of the typical problems. I will gather some problem from various sources, and I'll try to create a list of all such problems. So we'll try to solve them together. Okay. So then I will upload the video and this material by today to tomorrow today night. You can access that tomorrow. So then we'll meet then next week. Bye. I'm stopping the sharing.
Bye, sir.
Bye.